Today we start a brand new unit called Algebraic Vectors, and it's a different way of representing the vectors that we studied in our last unit on geometric vectors. And this notation and this representation um, is better for doing quicker calculations, not quite as easy to visualize as geometric vectors are, but definitely a lot easier to do complex calculations with algebraic vectors. So you can imagine, the beauty of doing the geometric vectors first is you get a concept of what those vectors actually represent, and you can visually see them. And the algebraic vectors take it to the next level and allow you to do some of the representation without the visuals. But you need that visual base in order to understand algebraic vectors. So we're going to start by looking at this example here. So in example 1, we have vectors that are given in terms of their components. And you'll see what a component is in a second. But let's imagine a vector now is placed on a Cartesian plane. So I've taken away the x-axis and the y-axis here, and I've just considered the points. So this vector starts at the point a, negative 6, 1, and travels along the Cartesian plane to the point b, 5, 8. So you can see the visual geometric vector right here, but we're going to represent it with some algebraic components. So if it travels from here to here, then what we say is vector AB is said to be B minus A. And just like if you're traveling someplace, if you want to figure out the distance that you've traveled, you would figure out where you are now and subtract where you began. Okay, so if you were thinking, Kingston is 100 kilometers from here, and Napanee is 50 kilometers, then the difference between those two, if you were traveling from Napanee to Kingston, would be the 100 where you are now in Kingston, subtract the 50 in Napanee, and that difference is the vector that you traveled, the 50 that you traveled from Napanee to Kingston. So the idea here then is instead of representing the vector with an arrow, you're going to represent it with components. So how do we get this? Well, we do b minus a. So the b coordinate is 5, 8, and we're going to subtract the a coordinate, negative 6, 1. And really what it does is you have to compare how the x's got from A to B and how the y's got from A to B. So if we look at the x's first, they were at negative 6 and they went all the way to 5. So that's a distance of 11. 5 minus minus 6. So of course, when you hear the minus minus 6, you're subtracting a negative or subtracting cold, you add and you get to 11. And then how did you travel from 1 to 8? Well, you traveled 7 units in the y direction. And you can see that by 8 minus 1 being 7 units. And so now the vector AB, instead of being represented with this arrow where you actually have to geometrically draw it, is going to represent it by this component and an algebraic vector 11, 7. Now, we can say 11, 7 is from A to B because I'm talking about the vector A to B, AB. Okay? And this takes care of both its magnitude and its direction. And you'll see that in a second. It's also known as the position vector because if you placed the start of this vector at the origin, if you went and grabbed this and took it and put it at the origin, it would arrive at 11, 7 because the difference between negative 6 and 5 is 11 units in the x direction, and the difference between 1 and 8 is 7 units in the y direction. So you'll see that as we move over to the next slide. When we get here, and actually I think I'll go right down here and draw it before we talk about what's up there. So here is that same vector that apparently goes from the point 0, 0, the origin, to 11, 7. And I'll prove it by bringing in that old vector. So that old vector, if it was on the Cartesian plane, negative 6, 1 would be way over here, and it'd be up here, and 5, 8. So that vector right here, the vector can be anywhere it wants to be. It'll keep its length, its magnitude, and its direction. So if we just shifted this over to 0, 0 and put the beginning at the origin, it would end up at 11, 7. So we can describe this vector AB as the same as the vector OP because it starts here and goes to 11, 7. All right, so that's a great way of visualizing. And any vector we have then can be positioned at the beginning at 0, 0 and figure out where it goes, and that will describe any vector that we want. And that's an algebraic vector. So I could bring in a brand new vector like this green one here and start it here and go there, and let's make it a small one, but at this angle. So you could describe it as maybe 1, 5 or maybe 1, 4. Okay, and that would be a smaller green vector and in a different direction. And we can use then any of these coordinates to describe all the different possible vectors that exist in the world. Instead of actually having to draw long ones going in this direction or short ones going in this direction, we can say what its endpoint is, and that is the position vector. And that's the algebraic vector that we're talking about. Right. Now, if we do place that vector that we were looking at the origin, and we had the vector 11, 7, we can define something called I, which is a unit vector in the direction of the x-axis. A unit vector has magnitude 1, and so it would start here and go 1 over and no y value, so it's just 1, 0. Okay, and then similarly, we can describe something called the j vector, which would be on the y-axis. And again, its magnitude is 1. It just goes up 1 and in the y-axis. So it's 0, 1. These two vectors, I and j, form the base of something called two space. Now, you might not have heard of two space, but I know you've heard of two dimensions. Instead of saying two dimensions in mathematics, we're going to call it two space. Really, it just is a quicker way of saying space, two space, instead of two dimensions with all those syllables. So we know that if you are considering measurement, one space is length, right? Length doesn't have a width or anything like that. Just how long something is one space or one dimension. As soon as you bring a length and a width, you can imagine like a rectangle, that defines two space or two dimensions, length and width. And then you can keep going on and define three dimensions with a length, a width, and a height, and you'll get something called three space or three dimensions. And if you think of a cube exists in three-dimensional world. It's got a length, a width, and a height, and so those three things define a three space or three dimensions. But for now, we're just going to look at two space, and they're defined by these two vectors, an I and a j. All right, so could we describe this same vector 11, 7 that we got from the other question, 11, 7, could we define it in terms of I and j's? Well, sure we can. Think of our geometric vectors. If I wanted to describe this, I could say it's a whole bunch of I vectors plus a whole bunch of j vectors. So the question is, how many I vectors would there be? Well, there would be 11 of those because it goes from here all the way over to x equals 11. And there is 7 j vectors. So we could describe this vector like this, 11i plus 7j. And this is just a different notation for the exact same algebraic vector that we just call 11, 7. Now, one thing you'll need to point out is the difference between a vector and a point. And we'll get to that coming up. Okay, but right now this is describing a vector and this is describing a point. All right, so this 11i plus 7j is just the same way of describing this vector. But of course, we'll probably do this notation a lot quicker than writing out 11I plus 11 plus 7j. Now, I can prove to you that this is actually the same thing by saying 11 i's. Well, if I have 11 of these little 1 zeros, I would have 11 0. And if I had 7 of the little 0 1s, I'd have 0 7, and I add those together, and I would get 11 7. Okay, so there's a little proof of the fact that this and this mean the same thing. Now, what else can we do? Well, we can do all sorts of the other math that we had done before. So for example, we could find the magnitude of AB. So still dealing with the same vector, but I want to know how big it is. Well, think about what we had to do in the geometric world. We had to use like the cosine law or the sine law or whatever to try and figure out how long this vector was. Well, we can do it very quickly in the algebraic vector world, because this is just the hypotenuse of a right triangle with 11 down here and 7 there. So if I want to figure out how long this is, I can do quick Pythagorean Theorem. 11 squared plus 7 squared equals this squared. So the square root of this squared plus this squared will get me the answer. And so if I wanted to find the magnitude, or how long this vector 11, 7 is, I would do the square root of 11 squared plus 7 squared. This is going to be something that's going to be very handy. You'll be doing quite a lot of, and I'm going to be calling it the square root of the squares. Okay, that's just my way of saying, let's take the Pythagorean theorem of the vector, of the triangle that's created by this vector, and find the square root of the squares. Okay, but it's essentially just doing the Pythagorean theorem. And instead of going AB squared equals that, I'm going to take the square root and this all at once. So 11 squared is 121, and 7 squared is 49. Add those up, and we get 170, and I'm taking the square root of that. So I could go and punch that in my calculator and get that it's 13.04. And that is exactly how long this vector is. Okay? So there it is all again. All right, what else can I do? Well, I can find the vector BA. So I just found the vector AB, which started here and went to there. But what about the vector BA? Well, let's think about it. If this is AB, or OP, but in this case, but AB, what would BA look like? Well, it would go in the same direction, or sorry, it'd be the same size, but in the opposite direction. That means this whole thing would flip down and go down here. So you can imagine that if it's the same length, and instead of going 11, 7, it's going to go negative 11 and negative 7 and be represented way down here. All right, so BA is going to be negative AB. Well, if AB is 11, 7, I want the negative version of that. Well, what do you think I do here? It's like a little mini rainbow. That's going to be negative 11, negative 7. And that's how I can just describe AB. All right. So that is describing a vector in two space. Now, the advantage of algebraic vectors is allows us to talk about vectors in 3 dimensions. And here we are with a vector in 3 dimensions. And can you imagine trying to do these ones geometrically? Now, we used to have to actually draw these vectors 3-dimensionally. And there was a couple of days where you would practice that. But we don't need to do that anymore. It's not in the curriculum anymore. We're just going to represent it with algebraic components. Okay? So here you can tell we're in 3 dimensions because I've got this third coordinate. And you can imagine what that third coordinate is. If this is an x and a y, this is called z. And the z coordinate is coming out of the page. So you can imagine that if you had your Cartesian plane x and y sitting right there, the z axis comes straight out of the page. Okay? And this vector goes from -2, -6, 9 to 5, 8, 7. I don't need to really worry about what that actually physically looks like, although I imagine it probably, is coming out of the page to my left or something like that, from my left to my right. But all I need to do is do the algebraic representation of this. And it's exactly the same as if we're in 2 dimensions. So if I'm going from A to B, remember that means B minus A. So I have to take all the components of the B coordinate and subtract all the components of the A coordinate. So B is 5, 8, 7, and I'm going to subtract -2, -6, 9. And I'll get my vector for B or AB. So first I'm going to go 5 minus minus 2. So just hearing that minus minus reminds me that I'm adding, and it's 7. And you can imagine the distance between this x equals -2 and 5 is 2 gets me back to 0, and then another 5 gets me to 5, and so that's 7. What about the y's? 8 minus minus 6 is like plus, so that's 14. And 7 minus 9 is -2. And again, this would be describing from A to B. Now, remember I talked about the difference between a vector and a point. Okay, so you'll hear this in a couple of my other videos later on. This is a vector because I am describing, one, you can see the notation here with a little vector symbol, and I describe it with an AB, and it equals this. So this is describing a vector because it's equals and the vector symbol. If there's no equals and it's just a single point or a single letter, then that's a point. So make sure we recognize the difference between a point and this whole thing, a vector. All right? And so if we put this vector at the origin, it would go to 7, 14, and -2. So actually I visualized it wrong. It would go along the x-axis 7, it would go up the x-axis 14, and -2 would actually be down through your page. So you're actually looking away from it, and it's going away from you. Okay? All right. Good news is the same definition of I exists in the x-axis. But of course, if we're in 3 dimensions, we have to consider what the z is. So we have I, vector I, which is 1, 0, 0, and it's a unit vector in the direction of x-axis. The j vector still exists, except it's called 0, 1, 0 as the unit vector in the y-axis. And I imagine you can figure out what it is in the z-axis. We have a new vector called the k vector, 0, 0, 1, and it's the unit vector in the z-axis. So again, we can take this vector here and describe it as the components of I, j, and k. So if we write this in terms of that, we can see that we would go 7 along the x-axis, so we would need 7 i's, 14 j's, and -2 k's. So we could write this as 7i plus 14j minus 2k. And I don't even need to imagine what the picture looks like. This is a great representation of that. I can prove it by putting in my i's as 1, 0, 0, my j's as 0, 1, 0, and my k's as 0, 0, 1. See the rainbowing happening, and we'd end up with the same thing. That's just a proof that this and this represent the same thing. Now here's the beauty of algebraic vectors. I can calculate the magnitude of this vector. And I don't have to go off and try and picture it. I don't have to need the cosine law and the sine law. And actually, if you were trying to solve this, you would have to solve 2 different triangles using the sine law or cosine law or Pythagoras. But guess what? We don't need to do that. We can do this just by doing the exact same math as we did before. So if I want to find the magnitude of this vector, I can do the square root of the squares. And the great news is the Pythagorean theorem works in 3 dimensions. And that's all this is saying. So, but I'm going to call it the square root of squares. Instead of calling it the Pythagorean theorem, I'm going to call it the square root of the squares. So 7 squared is 49. 14 squared is 196. And -2 squared is 4. Add those up, and I get the square root of 249, which is, off the top of my head, 15.78. And think about how much easier this is than having to do that graphically. What else is great is that I can do all these complex algebra or geometric additions and subtractions that I would have to do before, all geometrically. So can you imagine trying to draw 3 of these u vectors, making it come out of the page or into the page or whatever, and then making it 3 times bigger, and then trying to subtract another one. So you're drawing all these really odd, there's a vector, and then here's another vector, but it's going down here, and there's my result, except this one subtracts, so I'm going to have to actually have it come back like this, and then there's my result, except this is it looks like a two-dimensional, but it's actually in 3 dimensions, and trying to figure all that out. We don't have to do any of that. We can just use our algebraic rules to solve algebraic vectors. And so if I'm taking 3 u's, I can write that as 3 u's. There's my components for u, and here's the vector v. Remember, I know these are vectors because there's the vector symbol and then equals. These are not points. These are vectors. All right, so let's find this new vector. So it's 3 of these. Well, if the original u is 3 to negative 4, what do you think 3 of them looks like? Well, that's right. You're just going to rainbow this 3. So if it used to go to 3, now it's going to go to 9 because it's 3 times bigger. If it used to go to 4, it's now going to go to 6 because it's 3 times bigger. And if it used to go to negative 4, it's going to go to negative 12 because it's 3 times bigger. So there's how I make a vector 3 times bigger. I don't actually have to draw the vector and draw 3 of them to make it 3 times bigger. I can just do this quickly here. And then to subtract v, I don't need to worry about the diagram or anything like that. I'm just going to subtract the v vector. And how do you subtract x's or u's and v's? These new vectors, sorry. You're going to subtract the x's, the y's, and the z's. So if I subtract the x's, it's going to be 9 minus 5, which is 4, and 6 minus minus 2. So you can hear that minus minus means plus, so it'll be 8. And then negative 12 minus 6 is going to get colder, so negative 12 minus 6 is negative 18. And there's my very quick answer to finding this complicated vector subtraction. Let's look at a final one here. All right, so now I'm going to ask you to add them and find the magnitude of the resultant. Well, again, I don't even want to imagine what the picture would be and how much, cosine laws and sine laws and Pythagorean Theorem I'd have to do. I can do it much quicker using algebraic vectors. So first, I have to add these 2 vectors. How do I add them? I add the x's, add the y's, and add the z's, just like I did the subtraction over here. So if I'm going to add these, 3 plus 5 is 8. My new vector is at 8. 2 plus negative 2, well, that's a 0. And negative 4 plus 6 is 2. And so my new vector, boom, is 802. I found that resultant very, very quick and easy. Now I got to figure out how long it is. Well, what do I do for figure out how long it is? The square root of squares. So it's the square root of 8 squared plus 0 squared plus 4 squared, or 2 squared, excuse me. So quickly I can go 8 squared is 64, 0 squared is 0, and 2 squared is 4. Add them up, and it's the square root of 68. That's the exact answer. You could actually go and punch that in your calculator and get 8.2. Sometimes I'll ask you to reduce this and leave it as a rational, because a rational square root thing is going to be more accurate than this number that I've rounded. But you could do that by, remember, it's your grade 11 simplifying. So find a perfect square that is a multiple. So 68 is the same as 4 times 17. And I can take the square root of 4, which is 2. And root 17, I can't do anything. So this would just be that answer simplified. And this answer would be more exact and more precise than that. All right. So I've introduced the idea. Oh, by the way, yes. You probably won't write this down. You'll be able to do a lot of this in your head. When you see the question, you can go 3 plus 5 and write this step down, or 2 plus negative 2 is get that and that and that. You might even be able to do the subtractions in your head without writing them down. So there's a very good chance when I give you this, you're going to go straight to this line, and then you probably won't write that out. You'll actually square them as you go. So you'll go 8 squared is 64 and go straight to this, 0 squared and 2 squared and then square root. So I fully expect you to probably go from there to there. All right. So that's enough of the algebraic vectors for now. There's a couple of questions that in the notes for you to practice, and really it's a new way to describe vectors and allows us to do much more calculations in a much quicker method. Good luck.